Welcome to Lecture 5 of Physics 506. In this lecture, we're going to be talking about squeeze states. The simple harmonic oscillator is an interesting system, not only because every potential, or nearly every potential, can be approximated by the simple harmonic oscillator near its minimum. It actually has a very close relationship to photons that we're going to be exploring later in the class. And as we saw with the coherent state had the same uncertainties for position and momentum, namely the minimal uncertainty of the ground state, as the simple harmonic oscillator has for the ground state itself. And that was something that we could easily understand because we were simply shifting the ground state wave function in position or momentum space, but preserving its shape, and so the uncertainty remains preserved. When we start talking about squeeze states, the question is, can we do better than that? Well, we know from Heisenberg that we certainly cannot reduce the product of delta x times delta p, but we can actually do a sneaky trade-off of the uncertainty. For example, if I found a state where delta x is multiplied by e to the minus lambda and delta p by e to the plus lambda, where lambda is a real number, then we can reduce the uncertainty in position at the expense of raising it for momentum when lambda is larger than 0. And if our goal is to measure the position x, then this might actually be a very advantageous thing to do. At the very least, if you think about changing lambda from minus infinity to plus infinity, because in the limit as we go to plus infinity or minus infinity, the uncertainty in position or the uncertainty in momentum goes to 0, which means we're in an eigenstate. This would be a situation where we can actually interpolate between the eigenstates of position and momentum, and just by varying this parameter lambda. And indeed, that actually happens, and indeed it is also really quite cool to be able to do that. Now, what you should be thinking about with regards to squeezing states is thinking about looking just at a simple harmonic oscillator potential where you squeeze the potential or you relax the potential. If you squeeze the potential, you're going to be localizing more in position, and that's going to be creating a squeeze state in position while you have larger uncertainty in momentum. And if you relax it, it'll be vice versa. You'll have higher precision in momentum and lower precision in position. So another thing that working with these squeeze states allows us to do is to really exercise working with our 5-operator identities. And as you know, practice makes perfect. So we're going to be using those identities throughout the lecture. Another way of thinking about the squeezing operator is to think of it as a generalization of the displacement operator, which was a linear function in the raising and lowering operators, to a generic quadratic one. And so the squeezing operator, S of C and eta, is equal to the exponential of minus C divided by 2, A dagger squared plus I eta over 2, multiplied by the product A dagger A plus A dagger, plus the complex conjugate of C divided by 2 times A squared. Now, both the parameters C and eta can be complex. And you might ask, why are we taking such an incredibly odd-looking operator? And the answer is that we want this squeezing operator to be unitary. So let's take a look at the Hermitian conjugate of the squeezing operator. When I take the Hermitian conjugate of an exponential, it's still an exponential, but it is an exponential of the Hermitian conjugate of the argument. Now, when I take the Hermitian conjugate of minus C over 2 A dagger squared, that becomes minus C star over 2 A squared, plus I eta over 2 becomes minus I eta over 2. The A dagger A plus A dagger goes to A dagger A plus A dagger when I take its Hermitian conjugate. And then the C star over 2 A squared becomes C over 2 A dagger squared. Because remember, I take operators and take them to their Hermitian conjugate. And if they're products of operator, I have to interchange the order of the operators. And the numbers get complex conjugated when I take the Hermitian conjugate. But now take a look at this operator. You see the A operator term, the A squared term, has a minus C star as opposed to a C star. And the A dagger has a C as opposed to a minus C. And the I eta has changed sign. So that's actually the squeezing operator with a minus c and a minus eta. Now, because the exponential of minus a minus capital A is the inverse of the exponential of capital A, even when capital A is an operator, this object is the Hermitian conjugate is actually the inverse operator. And that's exactly what a unitary operator is. The Hermitian conjugate is equal to the inverse operator. So by making this choice, which looked odd to begin with, we're guaranteeing that the squeezing operator is indeed a unitary operator. So that was the reason why we have this odd-looking beast that we are working with. That's the most general quadratic then written as an exponential in terms of the A and A dagger operators that is unitary. Okay? Now, again, the way that you can think of this is that we're modifying the kinetic and potential energy, and we're making the potential more confining or less confining, and that corresponds to extra squeezing in position or in momentum, depending upon how you're doing it. We also can think of this as a unitary transformation on our states, and we can always transfer that unitary transformation onto the operators, and so the operators go to U dagger OU, just like going to the Heisenberg representation for time evolution. So we're going to transform our operator A into S dagger Xi eta A S Xi eta. And because we know that S dagger is the inverse and the inverse has just the negative parameters, it's an S of minus Xi minus eta A S of Xi eta. And now you can see that actually is a Hadamard transformation. So let's go ahead and evaluate that Hadamard. This is a situation where the Hadamard is not going to truncate at a single or a few terms, but what we are going to find is that the Hadamard gives us a pattern that repeats. So let's go ahead and calculate that first commutator. I have to put that exponent of the squeezing operator and take the commutator with A. Of course, A commutes with A, so it's only the A dagger terms that are not going to commute with the A operator. And we know what the commutator of A dagger with A is. It's just -1. So using our Leibniz rule, we can go ahead and calculate that first commutator, and we find it is equal to C A dagger minus I eta A, and then there's an overall minus sign because that Hadamard had a minus sign out in front that was multiplying the exponent of the squeezing operator. Now, if I take that operator, you see it's a linear operator in an A dagger and an A. If I take the commutator of that with the exponent of the squeezing operator again, I'm going to also get another linear combination in terms of the A and the A dagger. It's a little bit more complicated, but what you find is you get a +1/2 of a Xi times the commutator with the A dagger, which ends up being a Xi star A plus I eta A dagger, minus an I eta times the commutator of the A, but we already worked out what that is. That's a C A dagger minus I eta A. So you plug both of those guys in, and now you combine the terms that have the A daggers and the terms that have the A's in them. And what you see is that the A dagger terms are a plus I eta Xi and a minus I eta Xi, and those guys actually cancel. So you get a pure A operator term, and it has a modulus of Xi squared minus eta squared. Okay, now the fact that the second nested commutator gave me a number times the A operator means that this whole thing is going to repeat. And what we mean by that is, we started off with an A operator that we took the commutators of, and now we got back to an A operator again. So the next term will have this extra factor of Xi squared minus eta squared multiplying it, but then we get the same commutator with the A, and then when I take the second, which would then be the fourth nested commutator, I will get another factor of Xi squared minus eta squared times the A, and so forth. We can write down what the full result is by gathering the even and the odd terms. The even terms have just numbers that multiply A. It will be 1 plus a half Xi squared minus eta squared plus 1/4 factorial, Xi squared minus eta squared quantity squared, and so forth. And then the odd terms are going to have minus the quantity Xi A dagger minus I eta A times 1 plus 1/3 factorial Xi squared minus eta squared plus 1/5 factorial Xi squared minus eta squared quantity squared, and so forth. Now what I want to do is I want to remind you of what hyperbolic functions are. So the hyperbolic trig functions, cosh y is the sum m equals 0 to infinity y to the 2m over 2m factorial. Sinh y is the sum m equals 0 to infinity y to the 2m plus 1 over 2m plus 1 factorial. And that means that after this Hadamard, I can see that the term that involves the even guys transforms a to cosh the square root of c squared minus eta squared. And the odd terms will all go like sinh the square root of c squared minus eta squared divided by the square root of c squared minus eta squared, because I'm missing one power of y in that expansion. And then it's multiplied by this minus quantity c a dagger minus I eta a. So we've actually now summed that infinite series of the Hadamard because it created a repeating pattern. Now, if you're having some trouble seeing that we actually managed to do this, please pause the video, maybe even go back a little bit in the video, write out that Hadamard yourself, write out a couple of the terms, group them together, and make sure that you verify that this transformation is what occurs, because this is a very important result, and you want to make sure that you really understand what that result is. So it's an important result. We put it in a big box. We find that the similarity transformation S dagger AS is given by A times the hyperbolic cosine of square root of c squared minus eta squared plus I eta over the square root of c squared minus eta squared sinh of the square root of c squared minus eta squared minus a dagger times c over the square root of c squared minus eta squared sinh the square root of c squared minus eta squared. Okay? Now, we worked hard to get that. Do we have to work hard to get the transformation of the a dagger? Turns out, no, we do not, because all we have to do is take the Hermitian conjugate of this, and it will give us the result for the a dagger. So that's going to go inside a box as well. We're going to find S dagger, A dagger, S is just minus A C star over square root of C squared minus eta squared sinh square root of C squared minus eta squared plus A dagger, cosh square root of C squared minus eta squared minus I eta star over the square root of C squared minus eta squared sinh the square root of C squared minus eta squared. Again, be very careful to understand that taking the Hermitian conjugate of the top boxed equation gives the lower boxed equation. That's because when I take the Hermitian conjugate of a product of operators, I have to reorder the product. I have to put them in reverse order. And indeed, that then gives the transformation that we need. All right. You can look back at some of those expressions that we derived with Pauli matrices. This is very similar to those expressions, except here we have hyperbolic sines and cosines as opposed to sines and cosines, which is what we were getting with the Pauli matrices. It turns out there's a deep reason for that. The group that we're working with here is the symplectic group of 2 by 2 matrices as opposed to the SU2 group of orthogonal matrices, 2 by 2 matrices. All right. Now, we're going to look at the operator S of C and eta acting on the ground state. We're going to call that the state C comma eta, and that has a generic name called the squeezed vacuum state. We can now look at expectation values of the position and momentum operator within that squeezed vacuum state. We're also going to look at expectation values of the square of position and momentum. We now move the S operators from the ground state onto the X operator. And because I can write the X operator as the square root of H bar over 2m omega, A plus A dagger, we can use the results we just derived for the transformation of A and A dagger to work out what the expectation value is when I look at the position operator in the squeezed vacuum state. To do this, because these expressions are long, we're going to define kappa to be this combination of cosh plus I eta over the square root sinh of the square root, and lambda to be c over the square root sinh of the square root. And then because S dagger AS is kappa A minus lambda A dagger, and S dagger A dagger S is minus lambda star A plus kappa star A dagger, we can immediately compute the expectation value of X in the squeezed vacuum state. We'll get a prefactor of square root of H bar over 2m omega 0. We'll get a kappa A minus lambda A dagger minus lambda star A plus kappa star A dagger. Now, of course, the expectation value of A on the ground state and of A dagger on the ground state when I operate it to the left it's equal to 0. So that expectation value is equal to 0. The squeezed vacuum does not translate my state away from 0. But when we look at the expectation value of x squared, there we have to actually square these operators, and we're going to get cross terms. So we're going to have an a squared term. That's going to have an expectation value of 0. We'll have an a dagger term. That's the one that's not 0. We'll have a, I'm sorry, that second term should, I think should be a dagger. And then we'll have an a dagger squared term. And those two guys are equal to 0. The term with the a dagger, I can rewrite that as a dagger a plus its the commutator of a with a dagger. And what you're going to see there is that when I take the commutator of a with a dagger, that just equals 1. So we're going to just pick up that second term. Remember, there's a typo. That third term should be a dagger a, not a dagger. I will fix that in the notes for you. And we then get kappa minus lambda star times kappa star minus lambda. And when you go ahead and work that out, you get mod kappa squared minus 2 real kappa lambda plus mod lambda squared, and the whole thing times h bar over 2m omega 0. Now we can do the similar thing with momentum. For momentum, expectation value of momentum, because it's a linear function in a and a dagger, again gives me 0. Expectation value of p squared. Again, I'm going to have just one term that contributes, the a dagger term. I evaluate that by rewriting it as a dagger a plus the commutator, and it's only the commutator piece that's going to contribute. That gives me a term that's proportional to kappa plus lambda star times kappa star plus lambda, and essentially all I do is I change the sign of the term, so it's now plus real part of kappa lambda, and the prefactor, I believe the prefactor should be different. So I think that might also be a typo, because it should be h bar m omega 0 over 2. So there's a typo there on the prefactor as well. I'm sorry, I'll get that fixed for you in the notes. The prefactor should be h bar m omega 0 over 2 in both the expectation value of the p operator and expectation value of the p squared. I will correct that in the notes that you get. All right, so now what we're going to do is we're going to consider the special case of eta equals 0 and c equals r e to the I phi. We often find that working with squeeze states, setting eta equals 0 is a valuable thing to do, and it just makes a lot of equations simpler. Then if you plug in the definitions of kappa and lambda, you'll find kappa is equal to the hyperbolic cosine of r, and lambda is equal to the hyperbolic sine of r times e to the I phi, where r and phi are real numbers. Now plugging into the uncertainty for this particular squeeze state, we get delta x quantity squared is h bar over 2m omega 0 cosh squared minus 2 cosh r sinh r cos phi plus sinh squared. I can rewrite that in terms of the double angle formulas for hyperbolic functions as cosh 2r minus sinh 2r cos phi. And similarly, delta p squared is h bar m omega 0 over 2 times cosh 2r plus sinh 2r cos phi. Now if we go ahead and examine what this looks like when phi is equal to 0, we find we get cosh 2r plus sinh 2r. That's just e to the 2r for delta x, and we'll get cosh 2r minus sinh 2r. That's just e to the minus 2r for the delta p. I'm sorry, I have that wrong. That's going to be what I get for the delta x, and the cosh 2r plus sinh 2r is what I'll get for the delta p. That means the delta x is squeezed by e to the minus r, and the delta p is expanded by e to the r. And we get the vice versa of that. We get the exchange of that when we let phi equal pi, because the plus signs become minus signs in that case, and it is reversed. All right, so the product of the uncertainties is unchanged because that e to the r, e to the minus r term cancels, but we have a trade-off in which uncertainty is smaller between x and p, and it varies as that angle phi varies. Now note, it's very important to recognize that when phi is at some other value, the uncertainty product is typically bigger than h bar over 2 when phi is not equal to these magical numbers of 0 and pi. That is something that often gets gets remembered incorrectly by students when they're first working on this. So I get the minimal uncertainty state only in the case where phi is equal to 0 or phi is equal to pi. For other values of phi, my uncertainty actually grows in this squeezed vacuum state. All right, you're going to explore these ideas a little bit further in the homework. Now, the last topic I want to talk about is how we determine the squeeze states themselves. And to work with this, we have to go back and look at a Lie algebra, which is a Lie algebra of the symplectic group. We worked with the algebra for the generators of that Lie algebra in the first homework, and I just want to remind you what those were. We found the commutator of k0 with k plus minus was plus or minus k plus minus. And we found the commutator of k plus with k minus was minus 2k0. It's only that minus sign that is different from the SU2 Lie algebra. Now, we claim that choosing k plus equals 1/2 a dagger squared, k minus is 1/2 a squared, and k0 is 1/4 a dagger a plus a dagger actually produces this algebra. So let's go ahead and check that. Let's calculate k plus k minus. So plugging in what the definition of k plus and k minus is, I get 1/4 commutator of a dagger squared with a squared. We're going to use the Leibniz rule. We're going to find by first pulling an a dagger out to the left and an a dagger out to the right. I get 1/4 a dagger commutator of a dagger with a squared plus commutator of a dagger with a squared times a dagger. Now to calculate the commutator of a dagger with a squared, I use Leibniz again, pulling an a out to the left and an a out to the right. I now have 4 terms. But the innermost commutator is the commutator of a dagger with a, and that's just equal to -1. So I'm going to get a -1, and then I have to collect the terms that I have left. I'm going to get an a dagger a times plus an a dagger a, so I get 2 a dagger a's, and I'm going to get 2 a daggers. So I'm going to get a -1/2 a dagger a plus a dagger, and we go and look up what is the definition of k0. And if I go look up at what the definition of k0 is, you see that's -2k0, and indeed that's what the algebra is supposed to be. We can go ahead and calculate the commutator of k0 with k plus. Again, it's just using Leibniz rule again. And when you go ahead and do that, you find that it is equal to plus k plus. And when you do the commutator of k0 with k minus, you find it is equal to minus k minus. So we do get this symplectic Lie algebra from this representation, just like we claimed. And that means that we can write this squeezing operator as the exponential of minus ck plus 2 eta k0 plus c star k minus. And because we have a representation of that Lie algebra using 2x2 symplectic matrices, we find that we can factorize that as e to the minus lambda over kappa star k plus, e to the minus 2 log kappa star k0, e to the lambda star over kappa star k minus. And that was a homework exercise using exponential disentangling that you worked through. Now, for us, when we plug in what that product is in terms of the operators k plus, k0, k minus, because we derived it using 2x2 matrices, but because of the group theory, we can replace those 2x2 matrices by the operators. We find that the squeezing operator can be written as e to the minus lambda over 2 kappa star a dagger squared, e to the minus 2 log kappa star times 1/4 a dagger a plus a dagger times e to the lambda over 2 kappa star a operator squared. Now, if we operate that on the vacuum state, because the a operator annihilates the state, e to the lambda over 2 kappa star a operator squared acting on the vacuum is just replaced by 1. Furthermore, the vacuum state is a eigenstate of the number operator. So the expectation value of a dagger a, or the operator a dagger a acting on the ground state, is equal to 0. And then the operator a dagger is just equal to the operator of a dagger a plus a commutator. And you find that that's going to actually just equal 1 when it acts on it. So that middle term is going to go to e to the minus 2 log kappa star times 1/4, or e to the minus 1/2 log kappa star. And finally, I'm going to be left with the e to the minus lambda 2 kappa star a dagger squared term. There's nothing I'm going to be able to do with that. We're going to actually work it out in the special case where eta is equal to 0. In that case, c is equal to r e to the I phi, kappa is equal to coshar, and lambda is equal to e to the I phi sinh r. And when all the dust settles, using all of that work that I have shown you, what you find is that this squeezing operator acting on the ground state goes like 1 over the square root of coshar, that comes from the middle term, times the exponential of minus 1/2 e to the I phi tanh r times a dagger squared, that whole thing acting on the vacuum state. Now, I can go ahead and expand that exponential in a power series, and you get that the squeezed vacuum state is 1 over the square root of coshar, sum m equals 0, minus 1/2 e to the I phi tanh r raised to the mth power, square root of 2m factorial divided by m factorial, times the state 2m, because the a dagger is appearing as a squared operator, and I only get even number occupation states present in the summation. The square root of 2m factorial is coming from a multiply by 1. To convert an a dagger to the 2m, I need to divide by the square root of 2m factorial to make that into the state 2m. Okay, so you should be able to understand all the terms that appear in that summation. And that's a complicated expression. There's no way you could have guessed that. And there's no simple way of deriving it from the exponential form when you think of it in terms of the exponential of the squeezing operator, because the a and a dagger operators get mixed together, and it gets very complicated to try to work that out in the general case. Exponential disentangling gives you the easiest way to getting towards this operator identity, although there are other ways that you can do it. Okay, we also can look at a displaced squeeze state, which would put the displacement operator after the squeezing operator. That's the normal way that it works. You can also think of doing the displacement first and then the squeezing, but those two states are not in general equal because the displacement operator and the squeezing operator do not commute. But you could figure out what the c prime, eta prime, and alpha prime are in order to give you the same state. That would be an operator. That would be an exercise in working with these operator identities. It does get a little bit messy, and don't worry, I'm not going to ask you to do that. Okay. Now, the time dependence of these states is easy to work out because of braiding. So we just operate e to the minus I ht over h bar on this state, but I can bring it through using the braiding operation or the exponential reordering operation. And just like we did with the coherent states, you find you get a term e to the minus I omega 0 t over 2 that pops out, and the c term goes to c e to the minus I omega t. The eta term actually ends up not changing because it has an a dagger or an a dagger a in it, and those guys, when I move the Hamiltonian operator through, they don't change anything. Now, note that this c parameter is now going to change periodically with time, but the eta parameter does not. So it turns out that the operators a dagger a and a dagger are constants of the motion, which is why that eta term remains constant. Now, I would like to just take a moment and show you on Wikipedia what this looks like. I showed you the coherent state. With the coherent state, we had it oscillate back and forth. This is a squeezed coherent state that's oscillating back and forth. With the coherent state, it oscillated back and forth, but the shape did not change. Now here with a displaced or a squeezed coherent state, what you see happen is it broadens and squeezes. So this is a particular selection of parameters that squeezes at the maximum amplitude of the harmonic oscillator, and it broadens in between. And I find it almost hypnotic looking at this because you really can sort of get a feeling for how the squeezing is operating because the whole thing is slowing down at the maximum amplitude. There also is a similar state that is squeezed in the middle of the motion, and it's broadest at the maximum and at the minimum of the motion of the simple harmonic oscillator. But I thought it was pretty cool to show you what that squeeze state looks like. All right, we have one last thing to talk about. You know, these things aren't really worthwhile if we can't actually generate them. So an interesting question is, how do we generate coherent and squeezed states? Now, in general, this is not so clear. But for light, we can find that all classical sources of light are automatically coherent states. So that was easy. Now, squeezed light actually takes a fair amount of work. You need a nonlinear optical medium in general to create a squeeze state. And this was worked out in the mid-80s. And it's now understood how to do this. And so it's rather standard lab technique. Working out how to do it for other systems like atoms trapped in an ion trap is, of course, still not so simple. But of course, I don't think that that should really bother you so much, because you probably never asked the question, how do I actually create energy eigenstates, say, for a simple harmonic oscillator? That's also not that easy to do. It's not that easy to put a system into a pure energy eigenstate. And that didn't bother you. So you shouldn't be bothered by the fact that creating a squeeze state might be hard, because there are other familiar states that you're used to working with that creating them in an experimental lab might be difficult to do. Okay, so as I'd mentioned before, we can also squeeze and displace the vacuum, but we can also do that to excited states. But in general, that ends up not being very useful, and it really does complicate the formulas. So I'm not going to say very much more about that. And again, don't worry, I'm not going to have a homework exercise for you on that. The squeezed vacuum plays a very important role in improving the accuracy of LIGO, which is the detector for gravity waves. And that is going to be the last thing that we do in the class, is actually understand how LIGO works and why you need squeeze states to improve the accuracy. It actually improves the amount of the universe that you can see gravitational waves from by about a factor of 2. And by working with an even better squeezed vacuum, they can even improve that more and use, with the same device, just by putting in a squeezed vacuum, they can be sensitive to a much larger portion of the universe for gravitational waves, which is a pretty cool thing. Okay, we've reached the end of the lecture. In the next lecture, we are going to be looking at the factorization method of Schrodinger. This is a technique that I'm almost certain you have never seen, but it will generalize how using the operator method for the simple harmonic oscillator can be used for other classes of Hamiltonians, including the Coulomb problem for hydrogen and other problems that we're going to be exploring in the class. Take care.